Today I'm going to take off the circuit board on the head on the X gantry and probe around to see if I can find the connections for the end stops and that depth sensor. It should be pretty easy. I'm looking to reuse as much cabling as possible where practical, so this would be very handy if I could find all of these connections and then wire them through to the new controllers. I think I might need to take that off. That's the air assist. Maybe just loosen it so I can get the Allen key in. Okay. The plunger is there. Zoom in a bit. Plunger is just there. You can see it move. And that, okay, that moves next to that there. That is going to be a Hall effect sensor. That there is going to be a Hall effect sensor, and I guess what looks like a bolt on top that looks very rusted is probably a magnet. Have I got anything? Yep, that's magnetic. So it uses a Hall effect sensor on the plunger. Nice and simple. I can reverse engineer that, figure out the connection to the Hall effect sensor on that ribbon cable. It's just dropped down. I've just thought that second chip there is probably also a Hall effect sensor, because right in the corner at the end of the carriage there's a turret with a magnet in it. Yep. So that second sensor there determines the limit. So this here uses a optical encoder. The strip of plastic that goes along the gantry there has apparently extremely fine markings on. They look great to my eyes, but I'm sure if I zoom in they're probably small lines. The optical sensor reads those to determine the position, which is why the X gantry motor doesn't have anything other than power going to it, because it directly reads those lines to figure out its position. So the Y gantry motor here does have power and some sort of feedback, several data lines, which I'm guessing it uses to track the position. However, it also has one of those optical sensors down the back there. If I put my hand under here, I can feel exactly the same plastic strip that there is across here. This board here that we didn't know what was, that is connected to this ribbon cable that goes down, we've no idea what it does. I'm guessing it is exactly the same. It's got an optical sensor and it reads the position. So I was wrong in thinking that it used the feedback from the motors to determine the position. It actually has two completely independent position monitoring circuits. I'm guessing the the motor drivers that this thing use those pulses in some way. If it doesn't, they must go into the actual controller board, the main computer, and it must read those and determine how to change the speed of the motors through the motor controllers. Either way, I do not need either of those sensors, because stepper motors in themselves know exactly where they are because they're controlled precisely. So I don't see a reason to take those strips out. It's just dismantling for dismantling's sake. They're fine where they are. I just will never wire them up. I'm going to use this top board. I've just checked the pinouts on it, and we've got power and ground, one reader for the Hall effect sensor, the magnetic sensor that uses the plunger, a second one for the Hall effect sensor magnetic sensor that determines the end stop on the left. I'm guessing that it hasn't got a right end stop here, which is quite usual. What they would do is they would home to the left, and then because they know their position and they know how big the machine is, it will never run it past the right hand stop. I'm still not sure where the y-axis end stop monitoring is. I can't find that anywhere. I can only imagine that maybe one of these pins that goes down to read the positioning also has a Hall effect sensor on it, and there's a magnet somewhere I can't see. No, that's a bit of fluff. Because currently I cannot find a magnet. Oh, I've just found a magnet. Okay. Embedded into the rail down here that has the position sensor on, there is a tiny magnet stuck into the side. Okay, so there's a Hall effect sensor in this board too. I think with a bit of probing I can figure out what it is, which is great, which means both Hall effect sensors for the X and Y gantry come through this ribbon cable. Not so great that I'm probably not keeping the ribbon cable, because I don't think it's got a high enough, I don't think the connectors are big enough to give enough current for the steppers. However, it gave enough current for the existing motor, so maybe. I think the next thing for us is to take out all of the old wiring. I'd like to keep the wiring on the motors as much as possible, because it might be something we can sell. For instance, that there. Oh, okay. Now that's interesting. Remember I said this motor has feedback? It was not connected to anything. So I'm guessing this is a standard motor that has got some sort of feedback in it, rotary feedback maybe, rotary encoder. However, they're not using that, they're just powering it just like a normal brushed motor, and they're using the optical sensor on the side to determine its position. Oh, that is really interesting. Yeah, it was literally not connected to anything. There is no other cables going into that cable run. Okay. So as I was saying, we're going to take out the motors and the cabling on the motors, see if we can sell those. Some people might need them as replacements for theirs. I'm not going to use them again. And then we'll start stripping out some of the cabling and the main board. I've changed plans slightly. I bought a G-code controller. G-code is a standard CNC language that computers can talk to controllers like this to move them. I was going to buy a Ruida brand DSP controller at £325, but my thinking is for £35 I can get a G-code controller board, which I can run off a mini computer. I have a couple of mini computers spare. I can put the mini computer actually inside this machine, put a screen on the wall, and we can use it like that. Now, that's great for hobbyists if you're not using it very often, and it will work perfectly. It also means that the copy of Lightburn, the software I currently use, or used to use, that I already have a license for, will control that board. If I go for the Ruida controller, not only is it £325 on top, it is also another £90 on top of the license for Lightburn to enable it to control those more advanced controllers. But on the plus side, those advanced controllers are really good at operating the machine standalone. So you could turn it on, plug a USB stick in it, or just use the library that's built into the controller, all the things you've cut before, press go and it will cut things. No need to boot the computer, no need to use keyboard and mouse, no need to use the Lightburn software to load a file and to run it through the printer. So I'm going to work with the G-code cheap controller board to start with, and if that suits me, I'll keep it. If I find I'm using this machine more and more, or even going to a point where I'm doing some sort of production runs for friends, maybe I'll upgrade to the more expensive board. Okay. One of the next things I'm going to do to test is we need to come back to the laser. We know it's not working. We know it had a fault, which was a reflective RF fault, meaning anything from the lens is dirty to the entire tube has collapsed inside. What I want to do is, because we're turning it on at full power, some people on the internet suggest that they're now never supposed to run at full power, and running them at full power will create a feedback which will trigger that fault. So what I want to do is I want to create a small circuit that can do a 50% duty cycle or a 25% duty cycle, pulsing it on and off very quickly, which is how they work. to see if it actually fires the laser. So I might build that tonight, and tomorrow lunchtime I will try, see if it works. Okay. I wanted to trace all of the cables at this point to determine what the Hall effect sensors are connected to, so I could reuse the connectors in the future possibly. So I spent about 20 minutes with my probe, and I found the ground and the 5 volts feed to these gantries. Then I checked the pins and found that the Hall effect sensors would drop from 5 volts to 0 volts on certain wires when they were triggered. This was the plunger being pushed up, the X gantry, and I couldn't find the Y gantry end stop. However, the header board that plugs into it, I initially plugged it in incorrectly, which meant I was shorting a couple of the pins across. I think I may have blown the Hall effect sensor on that, because the pins make complete sense with a 5 volt feed, a ground, 2 pins for the optical sensor, which I actually tested and they work, and then 1 pin that permanently gives 5 volts, which must be the Hall effect sensor. So I think I've broken that, which means getting that circuit board out that's buried in the gantry next to where the motor came from. I'll try that at some point when I'm ready to fit the new motor and replace that chip. Otherwise, I would need to fit a new end stop on the Y gantry. This is actually quite interesting. If I put the probe of my mini oscilloscope onto the pin from the optical output on the Y gantry and move it, you can actually see the frequency of the feedback from that sensor. Even moving it this slow, it's coming in at 100 times a second. I believe that there is probably, I don't know how the sensors work, they both seem to obviously give a pulse, a digital pulse. I can get about 85 Hertz moving it slowly, and similar on the other pin, so it might just be the same pin, the same signal. I just thought it was quite interesting.